So welcome to all. Myself Dr. Santhosh Singh, working as an Associate Professor in Department of Physics. Today I am going to discuss about occupation probability of carrier. In my last video lecture, I gave some discussion about occupation probability and carrier's density. Now today I will try to explore something more about occupation probability. Means how the charge carriers will take the place in particular energy levels. Okay, what are the probabilities so that any charge carriers will occupy any particular energy levels? So we will discuss something more about that things. So let's start. So we already discussed that the density of a state, rho e d, for any bulk semiconductor case is rho e is equal to 1 upon 2 pi square multiplied by 2 mc upon h cross square whole to the power 3 by 2 e minus ec whole to the power half for conduction band, and for valence band the density of state rho of E is equal to 1 upon 2 pi square 2 mb upon h cross square whole to the power 3 by 2 eb minus e whole to the power half. And what is the unit of this density of state? So the unit of this density of state in term of joule is number of state per meter cube by energy per unit energy range. From the definition you can derive this unit formula. So the definition of density of state is number of available energy range, number of available energy state per unit energy range per unit volume. So by definition you can derive this unit. So if you want to take all the quantity in MKS system, so your units will be number of states per meter cube divided by energy, means joule, or if you want to CGS system, the same thing will be converted as a number of states per centimeter cube per unit energy range, and that there the energy value will be in electron volts. So this is the density of state, and this is the density of state for quantum well structure. And see, this density of state is constant. So actually the density of state is very important for determining the charge carrier density or carrier concentration. Not density, carrier concentration. Okay, means number of available charge particle per unit volume of the given material. So you, with the help of these density of state formula, you can derive the expression for carrier concentration. Okay, so the density of state is important for determining, important term or quantity for determining the carrier concentration. And how this density of state will vary? It will vary in parabolically in both conduction band region as well as valence band region. So see here, N is carrier concentration, N, and that N formula is what? N is equal to NEDE, where Ne is what? Density of charge carrier. So if you want to calculate the carrier concentration, means total number of available carrier for any particular material, you have to integrate the density of charge carrier over entire available energy range for particular or for given material. So N, total number of available charge carriers, is equal to integral over NED. It is, this thing I already discussed in last video. So Ne, You know that this Ne will means density of charge carriers N of E is equal to rho of E multiplied by F of E. Okay. So this rho of E is what? The rho of E is nothing but density of state. That's why whenever I started all this thing, definitely I try to tell about density of state, because it is very, very important and fundamental properties of any given semiconductor. Once you know the density of state for given material, you can calculate all the things related to electronics. Okay, like what will be the charge carriers, or charge carriers, a total number of available charge carriers. Then based on that charge carriers, you can calculate the current. Even the optical property will be also governed by with the help of density of states, because for any optical property, the charge carriers will be populated from valence band to conduction band, and they make some transition. So the optical phenomena will happen. Okay. So where this transition will occurs? It will occurs in between the energy levels. So what will be the position of energy level? So that thing will be determined by density of state. Okay. Where are the chances of any available energy state, or for any allowed energy solution? All the thing you can see by the picture of density of state. That's why the density of state is very, very important. So see this. So in this Ne, density of charge carrier is equal to rho E multiplied by Fe. So this rho E is nothing but density of state, and this Fe is F of E is nothing but probability of occupation of charge carriers for particular energy E. Okay. So what will be the probability of any charge carrier, so that they can take the position in energy level E. Okay. So that is in another name, this probability of occupation can be also known as probability distribution function or Fermi-Dirac distribution function. Why? Because it is given by Fermi. Okay. So Fe is probability that state at energy E is occupied by any charge carriers. So you know that if you know the probability of any certain event, so if the event is very, very certain, definitely it will be happen. The maximum probability is 1. Okay. So if you know the probability of any event, and for this case, if it is F of E, so what will be the probability of such that those events will not happen? So for that case, for the event will not occur, for that case the probability will be 1 minus F of E. Okay. So F of E is probability of occupation, or F of E is the probability that state of energy E is occupied, and 1 minus Fe is the probability that state at energy E is unoccupied. Okay. So that's all the thing about probability of occupation. Now we will see how the charge carriers will occupied to any particular energy levels. What will be the variation? What will the variation happen for F of E? If we are going to plot the F of E, means probability occupation probability, or probability distribution function for any charge carrier. So we will see some drastic changes once we move from absolute zero temperature to some higher temperature. So that's the thing we will going to discuss. So see here, probability of occupation or probability distribution function, or probability for any charge carriers to occupy the energy level E is given by F of E is equal to 1 upon e to the power e minus ef by kt plus 1. Okay. So this is the Fermi-Dirac, this is also known as Fermi-Dirac distribution function for electron to occupy the energy levels. Okay. So based on this distribution function, we will discuss some things which are going to happen at lower temperature, means at absolute zero temperature and at some higher temperature. So if you are discussing the case for absolute zero temperature, means T is equal to 0 Kelvin. So just put this T is equal to 0, what happens? This whole function become e to the power infinity. So e to the power infinity is 0. So Fe is equal to 1. Fe is what? Probability. And if Fe is equal to 1, means that events will definitely take place. Charged particles will occupy the certain energy levels. Definitely. So at T is equal to 0 Kelvin, you know that from solid state physics, you know that the valence level, valence bands will be filled. And all the conduction bands levels will be empty. So if you are going to plot this f of E, means occupation probability or probability distribution function for charge carriers, what happens? Let's suppose this is your f of E on this y-axis, and on x-axis you are taking energy. So f, this is 1. So your any value of Fe, because it is probability, it will not exceed to 1. So if this is the case at particular energy, so you know that for at absolute zero temperature, if up to this energy level, all the bands are filled, and this energy level is known, up to this energy levels, all the energy value will comes under valence band region, because you know that at absolute zero temperature the valence band is completely filled, and the energy levels beyond the valence band, means any energy levels which are not the part of valence band, will be completely empty. There will be no charge carriers present or occupied for any energy level which will be not the part of valence band. So this whole region you can say is the part of valence band. So your probability function, see, in this case your probability function is a kind of a step function. It have a value 1 up to certain energy value. So up to this energy value, all the energy levels are filled, completely occupied. So you can say this is the valence band, and beyond this energy value, all the bands are empty. 0. Probability is 0. Means there is no energy levels available here so that the charged particles can occupy those energy levels. This is first case. Now at higher temperature, what will happen? See, this is the case when we are discussing that at T is equal to greater than 0 Kelvin, means at some higher temperature. So at some higher temperature means here this T will take some value, means this overall function Fe will give some lower value than 1. Fe will be always less than or equal to 1. Okay, nearly, for some higher temperature value. Okay, so what will happen? Some lower energy value, it will be nearly equal to 1. Probability value will be nearly equal to 1. But once you move the higher energy level, Means this value, if you are increasing this energy value at some higher temperature, see some smearing happen. So the curve will be like that. Okay. Means up to certain energy value, it's in this case also up to certain energy value, the probability of charge particle to occurs in these energy levels are 1. But after certain energy value, see here, this is 1, now decreasing little bit. So up to certain energy value, let's suppose this is E1, still the probability value is 1. But after this energy value E1, the probability is decreased. Means there are the chance that even a very small decrement occurs, but there are the chance that so that the charged particles cannot occupy these energy level. Okay. Now, suppose this is your EF, means highest field energy level, EF. Okay. Now, in this case, see here, even beyond this EF energy value, some probability exists for charged particles to occupy these levels. Okay. So this is the case, means some smearing happens. There are the chance that some available energy levels in balance band region will remains unoccupied, and there are again some chance that some energy levels in the conduction band will occupied at higher temperature, but that chance are very, very less. So that is the effect of temperature. And also how the Fermi function or probability of occupation function behave with temperature. Okay. See, the same thing is happen here more clearly. At some more higher temperature, this red line, the chance of empty levels in valence band is increased, means probability is get increased, but still there are some levels which are completely filled, means their probability is 1. But see, beyond this EF, there are still again some chance. This region is increased, means the probability will further increase for some higher temperature. In previous case, this red line is representing some higher temperature in comparison to this previous case. This case means if you are increasing the temperature, there the chance of occupation of charge carriers in conduction band region will increase. Actually, this is the probability. It will happen or not happen, that is another thing. But there are the chances, there are the probability. Okay. That is my concern. Okay. So, these all the things are written here. And also there are, Fe is the probability for occupation. So 1 minus Fe is what? 1 minus F of E is what? Probability of unoccupied level. Okay. So that will also increase. Okay. Here 1 minus Fe, you can say 1 minus Fe will also increase. Okay. So at higher temperature, higher energy state can be occupied, leaving more lower energy state unoccupied. So means 1 minus Fe will also increase. Okay. If Fe will decrease for this level, for valence band level, so if Fe is decreased, then 1 minus Fe will increase. Okay. So now let's discuss about some practical case which are already simulated. So here we are going to discuss about some curve about probability of occupation for silicon case, and for case of study they have taken the three temperature: T is equal to 10 Kelvin, T is equal to 300 Kelvin, and T is equal to 450 Kelvin. Okay, so this blue one is very high temperature, you can say. This T is equal to 10 Kelvin is nearly equal to the absolute zero temperature. T is equal to 300 Kelvin is comparison to higher temperature than T is equal to 10 Kelvin, but still a low temperature. So see what happened. So once the T is equal to 10 Kelvin, KT value is 0.0086 electron volt. See, once the T is equal to 300 Kelvin, K multiplied by T is 0.0259. Little bit increase. Once the T is equal to 450 Kelvin, the KT value is 0.039. Okay, at higher temperature. So see, Fe is what? Form of Fe is what? 1 upon 1 plus e to the power e minus f upon kt. And once the kt is increasing here, what happened? This overall value of Fe is decreased. Okay. So if Fe is decreased in valence band, 1 minus Fe will increase in conduction band. So see here, nearly to 0 Kelvin means for 10 Kelvin, this curve is nearly equal to step-like function. Means they are showing the perfectly all the bands up to this region is this energy range is completely filled because they are showing the probability 1. Here a small smearing you can say, means there are some chances so that some bands are maybe unoccupied. Okay. So once you are increasing the temperature, see there are some chances here. Here means here, see the probability, it will be less than 1. Okay. Up to here. And this is the 1/2 region. Okay. So from this energy value to this energy value, there are the chance that because the probability is less than 1, means there are chance that these levels are maybe unoccupied. Okay. But here again same thing. Here you can say for T is equal to 0 Kelvin and at this energy the probability for occupied is 0. Means there is no chance so that the energy level will be occupied. But once you are increasing the temperature, what happens? See, some smearing happen at this energy value. For the case of T is equal to 300 Kelvin, there are some probability value. Means there are some chance so that this region, this energy levels will be occupied. So same thing you can discuss for T is equal to 450 Kelvin, means this chance will be more increased. So if what you can conclude that if you are increasing the temperature, the chance of occupied the level in conduction band will increase and chance for unoccupied level in valence band will also increase. Okay. So same case for intrinsic case. So see here. Now here, this is the energy value E. You can say it is in electron volts. So at lower energy, see from this energy 0.4 electron volt energy, your all the energy levels are completely filled. Why? Because the probability is 1. But beyond this energy range, from 0.4 to 0. You can say 0.55, the chance of occupation of these energy levels which are present here is less than 1. Means there are some chance so that these levels may be unoccupied by charge carriers. And again, here you can say, if this is the part of conduction band, no, don't say this is the conduction band, because your conduction band is started from here. So even much below the conduction band, the probability for occupying the level it become 0. Okay. Here you can say, here from here onwards, the probability, this is the probability occupation curve, this blue line. So it becomes 0. Means from this region onwards, there is no chance. Why? Because probability is 0. So that the charge carriers will occupy any energy level. Okay. This is the case of pure intrinsic case of silica. Okay. Now donor case means if you are making the silicon as a N-type semiconductor. So see what happened. This is even less than 0.8 electron volt energy. But see here, the chance for unoccupied levels occurs at 1/2 electron volts. Means some layers are filled, are completely filled once you doped with some N type of impurity. See here, at 0.8 electron volt, the chance for occupation of charge carriers is completely 0. But here it is completely 1. Means up to this level, the chance for occupying the charge particle to energy level is completely 1. Means up to this level, the charge particles are completely filled. Whatever the smearing and all the thing occurs here in valence band, in conduction band region. Okay. There are here, even in conduction band, the some levels, there are some chances so that the electrons or charge carriers will occupy the energy levels in conduction band also. That's why the N-type semiconductor means the electrons are available in conduction band so that it will conduct. That is the effect of doping. Okay. But before, in pure case, there is no electrons available in conduction band. Okay. So these all are the things I want to discuss here for taking as a practical example which are simulated for silicon case. So that's all for today discussion. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.